Module 2, Lecture A, Understanding Datasets. By the end of this lecture, you will be able to describe the typical tabular structure of a basic machine learning dataset, distinguish between common data types such as numeric, categorical, and text, and evaluate simple datasets for obvious quality issues that could affect learning. Tabular dataset basics. Each row a case. In a tabular dataset for machine learning, each row represents one case or observation at a specific moment, such as a single survey response, transaction, visit, application, or sensor reading. The columns in that row store all the relevant information about that case. This consistent row and column structure lets algorithms compare cases in a uniform way. As a result, they can reliably detect patterns and relationships across the data. What counts as a single case in a dataset depends on the question you want to answer. In a customer churn dataset, one case might be a customer's status at the end of a billing cycle, while in a housing dataset, it could be one sold property, and in a medical dataset, it might be one hospital admission, even if the same patient appears multiple times. The crucial point is that the dataset designer chooses a clear, consistent unit of analysis so that each row represents a comparable example for the model. When working with datasets, make sure each row clearly represents one consistent case in the real world. Do not mix different kinds of units in a single row or spread one case across several rows without a clear purpose. Always check what a row stands for and apply that definition the same way throughout the dataset. This clarity helps you structure the data properly and build models that can learn accurate patterns. Feature columns explained. In a machine learning dataset, the columns are called features, and they represent measurable properties that describe each case. For example, in a hospital dataset, features might include age, blood pressure, and smoking status, while in a housing dataset, they might be the number of bedrooms or distance to the city center. These features supply the information that algorithms use to find patterns and make predictions. Without clear, well-defined features, even very advanced models cannot learn effectively. Feature columns in a dataset can be simple values like height or product price, or more complex values that are calculated from other data, such as body mass index or average spending. These features may be directly observed or derived, but in all cases they add different dimensions of information. For instance, in customer analytics, you might include purchases, spending, region, and marketing channels, with each one contributing a distinct perspective. Taken together, these features provide a richer, more complete view of the data than any single feature alone. Each feature column in a dataset has a specific role, with its own meaning, data type, and scale that affect how it can be used. For instance, a numeric and ordered feature like age supports meaningful calculations, while a categorical feature like country indicates group membership. In an online reviews dataset, features such as review length, star rating, and product category each capture different aspects of the data. Understanding these distinctions is essential for explaining how features are constructed, why they matter for the learning task, and for building accurate, interpretable models. Target column basics. In a tabular dataset for machine learning, the target column is the one that contains the outcome the model is trying to predict. Other columns hold features such as age or house size, but the target holds the actual answer, like a disease diagnosis or a house sale price. You can think of the target column as the learning goal for the model. During training, the model uses both the features and the target together to learn patterns, so that later it can predict the target from new data, where only the features are known. The type of values in your target column determines what kind of machine learning task you have. If the target is numeric, such as prices or lengths of stay, you are doing regression and predicting continuous outcomes. If it contains categories like spam or not spam, you are doing classification and assigning cases to discrete classes. In some problems, the target may be an ordered category or a probability score, such as satisfaction levels or likelihood of churn. Recognizing which type of target you have is essential for choosing appropriate models and evaluation methods. The target column in a dataset is critical, so you must understand exactly how it is defined and recorded. Often the target is not directly observed, but comes from human judgment, business rules, or outcomes that appear later, which can introduce subjectivity and delay. Even labels that seem simple, like whether a product was returned, may be handled differently across regions and become inconsistent. Any ambiguity or unreliability in the target column can mislead the model during training and reduce the accuracy of its predictions. Common data types. Numeric features. Numeric features are measurable values such as age, income, or temperature that play a central role in data-driven models. They have a natural order and meaningful differences between values, which makes them suitable for operations like averaging and analyzing trends. In datasets, numeric features capture real-world aspects like product purchases or travel speed and provide a solid basis for comparison and analysis. When working with numeric features, it is important to know whether they are continuous or discrete, because this affects how we interpret and model them. Continuous features can take any value within a range, such as height or time, and have infinitely many possible values between 2 points. Discrete features represent counts or steps, like the number of children, and change in fixed increments without fractions. Correctly identifying a feature as continuous or discrete helps you choose appropriate visualizations and modeling techniques, and shapes your expectations about patterns in the data. Numeric features can be represented and scaled in different ways, and these choices affect how they are interpreted in analysis. The same type of quantity, like temperature or income, can be measured on different scales or over different time frames, leading to different meanings. Some numeric features have a meaningful 0 point, such as $0, while others use 0 only as a reference level, as with certain temperature scales. Transformations like taking logarithms or standardizing scores change how algorithms perceive differences between values without changing the fact that the data is numeric. Being aware of these properties is essential for building effective data models. Categorical data basics. Categorical data consists of labels or categories rather than numerical values, and it answers questions like which one or what kind. Examples include countries such as Brazil or Japan, membership types like basic or premium, blood types such as A or B, and college majors like history or biology. These values are used to group or classify observations, not to perform arithmetic operations like addition or averaging. Recognizing this distinction is essential for correctly handling categorical features in machine learning. When working with categorical data, it is important to distinguish between nominal and ordinal variables because this affects how you model them. Nominal categories, such as eye color or product type, have no natural order, so their sequence is irrelevant. Ordinal categories, like education level or satisfaction rating, do have a meaningful order, but the gaps between levels are not numerically defined. Correctly identifying a feature as nominal or ordinal helps you choose appropriate encoding methods and interpret model results properly. When working with categorical data, it is important to consider cardinality, which is the number of distinct values a feature can take. Features with only a few categories are straightforward, but those with many categories, especially rare ones, can make storage and learning more difficult. Real datasets may also contain inconsistent labels, such as different spellings for the same category, as well as missing or vague entries like blank fields or a general other category. Carefully checking these issues helps you transform categorical data into a form that machine learning models can use effectively. Working with text. Text data, often called unstructured text, is made up of sequences of characters or words rather than numbers or categories, and includes things like customer reviews and social media posts. Even though it looks different from numeric data, it is still stored in similar table-like formats, with each cell holding a piece of text such as a sentence or document. The main difficulty is that the structure and meaning of this text are not directly visible to algorithms, so it requires additional processing before it can be analyzed effectively. Text data carries rich layers of meaning, such as sentiment and intent, and many words change meaning depending on context, which makes it challenging for models that work best with numbers or categories. To make text usable for these models, we convert it into numeric forms like word counts or more advanced encodings that capture relationships between words. Even after this conversion, it is important to remember that text has unique properties that are very different from simple numeric data, such as age or income. In many real-world data sets, text appears alongside numeric and categorical data, and should be treated as its own type because it has unique strengths and challenges. For instance, text in support tickets can reveal patterns like product defects that numbers alone might miss, but it can also add noise through errors and slang. Text fields may contain sensitive information, so they must be carefully cleaned, anonymized, and transformed before modeling. Overall, text features are powerful but complex, and simple statistics are not enough to capture their full behavior. Spotting data issues. Detecting missing data. When you open a dataset, you should always check for missing data, because gaps can weaken your model. Missing values may appear as empty cells or placeholders like NA, but they can also be less obvious, such as data recorded only for certain groups. For example, blood pressure might be collected for adults, but not children, or income might be recorded only for loyalty members. By scanning for these gaps, you can spot incomplete data and be more careful in how you analyze and model it. When you see missing data, you need to understand why it is missing, because this affects your conclusions. If values are missing at random, such as from a simple sensor glitch, the data loss is inconvenient, but usually not biased. However, if missing values are related to other variables, like higher earners being more likely to skip income questions, the results can become skewed. Clusters of missing data in certain groups or time periods signal potential bias and warn you that your model may be learning from an unrepresentative sample. When working with datasets, you must recognize when values are effectively missing, even if the cells are not empty. Placeholder codes like zeros or extreme numbers may indicate that information was not recorded, rather than true measurements. For example, a 0 birth weight or a credit score of 999 might signal missing data. To avoid misleading results, review the data documentation, look for unusual values, and compare distributions with and without these entries. Based on this review, decide whether to recode, impute, or exclude such records so your analysis reflects the real underlying data. Python code, detecting missing data. This script demonstrates basic techniques for detecting missing data using a very small, made-up dataset. Its goal is to highlight simple checks that beginners can easily understand and apply. By focusing on straightforward examples, it helps you recognize when data is incomplete and needs attention. Overall, it serves as an introductory guide to spotting missing values in a clear and accessible way. We begin by importing the pandas library, which is essential for working with tabular data in Python. Pandas offers powerful data structures called data frames that help organize and manipulate datasets efficiently. These data frames are especially useful when handling missing data, which is a key focus of this script. We begin with a small example dataset that has clear missing data issues. It has 3 columns: age, income, and city. The age values include valid numbers, a missing value, and a negative one that likely stands in for missing data. The income values include typical amounts, a missing entry, and a very large number that also seems to be a placeholder. The city values include real city names, along with entries like n/a and an empty string, which can also indicate missing data. This simple setup will let us demonstrate how to detect and handle these different forms of missing information. We use pandas to create a data frame from the dictionary of data, which organizes the information into a clear table. This tabular structure makes it easier to analyze and manipulate the data. It also provides built-in tools to handle missing values and placeholders efficiently in later steps. We begin by printing the dataset so we can quickly see its overall structure and check for obvious missing data. Viewing all rows and columns helps us spot anomalies or placeholder values that may indicate gaps in the data. This initial inspection is an essential first step that prepares us for more detailed data cleaning and analysis. This code uses a pandas function to check each column of a data table for missing values, then uses another function to add up how many missing entries appear in each column. The result is a count of missing values for every column. This gives a quick overview of how much data is missing across the dataset. We begin by printing a short message to introduce the next result, which is the number of true missing values in each column of the dataset. This output shows how many entries are missing for every column. Seeing these counts helps us understand how much data is incomplete before we do any cleaning. It is a key step for deciding where we need to focus our efforts to handle missing data effectively. We create a dictionary of placeholder values that tells us which entries in each column represent missing data. In the age column, the value -1 is treated as a placeholder. In the income column, the placeholder is 999,999. In the city column, both the text n/a and an empty value are placeholders. Defining these placeholders lets us later convert them into proper missing data markers, so the dataset accurately reflects where information is missing. We make a copy of the original data table before cleaning, so that any changes we apply do not affect the source data. This lets us try different transformations and corrections without risking damage to the initial dataset. By keeping the original version intact, we can always refer back to it or reuse it later if needed. In this part of the code, we loop through each column of the data frame and look for placeholder values that indicate missing data. For every column, we have a list of these placeholders, and we use a pandas replace operation to turn them into the standard missing value marker, called NA. By converting all these different placeholders into a single consistent marker, we standardize how missing data is represented. This makes it much easier to detect, analyze, and handle missing values later in the data processing workflow. After replacing placeholder values with proper missing data markers, the code uses a pandas function to recount missing values in each column. This follow-up check shows how many missing entries are still present after cleaning. By doing this, you get a clearer view of the dataset's remaining gaps and overall integrity. We first print a short message to signal that we are about to show the updated counts of missing values. Then we display how many missing entries each column has after replacing placeholder values with proper missing data markers. This lets us clearly see how much missing data remains and how effective our cleaning steps have been. The conclusion of the script stresses the importance of recognizing placeholder values that actually represent missing data. These placeholders can hide the true amount of missing information in a dataset. Because of this, It is essential to carefully inspect and clean data so that any analysis based on it is accurate and reliable. This script shows how to detect and handle missing data in a small dataset. It starts with a table that includes both obvious missing values and hidden ones represented by placeholders, such as special numbers or text for age, income, and city. At first, the tool only counts the clearly marked missing entries, so many gaps remain undetected. The script then replaces all placeholder values with the standard missing data marker and counts again, revealing more missing values. This process demonstrates why it is crucial to identify and convert placeholder codes so you can accurately measure and improve data quality. Detecting outliers. When you begin working with a dataset, an important step is to identify outliers, which are data points that are unusually large or small compared to the rest. These values are not always mistakes, but they can strongly influence machine learning models. For example, if most homes use between 100 and 1,000 kilowatt hours of electricity, but a few records show tens of thousands, those might be data entry errors or special cases like factories. If the model treats these extreme values as typical, it can distort its understanding of normal usage and lead to poor predictions. To identify outliers, look at the distribution of each numeric feature and use your domain knowledge to judge whether values are realistic. For example, a body temperature of 200 degrees, a negative age, or a billion-dollar house in a small town probably indicates a data entry error. Review summary statistics such as minimum and maximum values and compare them with what is physically or economically possible. Values that fall far outside reasonable real-world ranges are likely problematic outliers that can mislead your model. Recognizing true outliers is important because unusual data points can contain valuable information, so they should not be removed automatically. In some tasks like fraud detection, the rare and odd transactions are exactly what you want to find, and deleting them would undermine the analysis. In other tasks, such as predicting city commute times, extreme values caused by errors, like trips lasting several days, can mislead the model. Therefore, you must identify extreme values, and often with expert input, decide whether to adjust them, exclude them, or treat them in a special way so the model learns real patterns rather than data errors. Sampling and bias clues. When working with a dataset, you must be clear about who or what the data represents, because bias arises when the data does not match the broader population you care about. For example, a model built to predict customer churn for a global service may fail if it is trained only on North American users, and a medical dataset based mainly on middle-aged urban men will not represent children, older adults, or rural communities. These mismatches are not technical bugs, but they can seriously reduce a model's accuracy and fairness. So checking how well your data reflects the target population is essential. To spot potential issues in your dataset, look at how key features are distributed and review any information about how the data was collected. Check whether important subgroups, such as different ages or income levels in loan applications, are fairly represented, rather than dominated by one city or one type of worker. In product reviews, notice if most reviews come from a single language or a specific feedback program, which can also skew the data. These imbalances do not automatically make the dataset unusable, but they should prompt you to question how well it matches your model's real-world context and whether you need more data or adjustments. When working with a dataset, you should think about how it was created over time and what might have influenced it. Data from a short-term promotion, for example, may overrepresent price-sensitive customers and distort predictions about long-term behavior. Social media algorithms can create feedback loops that amplify certain content, and historical data can embed past biases such as discriminatory hiring or policing. It is essential to detect these biases early, understand how they affect your results, and adjust your models or seek more balanced data to improve fairness and reliability. Python code, sampling, and bias clues. In this lesson, we use a very small, synthetic customer churn dataset to highlight simple clues of sampling bias. The goal is not to build complex models, but to pay close attention to how the data is distributed. By examining these distributions, we can start to recognize when the sample may not fairly represent the broader customer population. We begin by importing two key Python libraries, NumPy and pandas, to handle data efficiently. NumPy supports fast numerical operations, while pandas offers flexible data structures such as data frames for organizing and manipulating information. These tools form the foundation of our work in this script, enabling us to generate synthetic data and analyze its distributions. We use a fixed random seed in the NumPy random seed function, set to the value 42, so that any random numbers generated will be identical each time the script runs. This makes the behavior of the code predictable and allows us to reproduce the same results in future runs. In other words, setting this seed ensures consistency and reproducibility in our experiments. We begin by choosing the size of our synthetic dataset, setting it to 40 customer records. This means we plan to simulate data for 40 different customers. Then we use a random integer function from a numerical library to generate ages for these customers. We specify that the ages must fall between 18 and 70. So each simulated customer is assigned a realistic age within this range. We create a list of regions for a dataset of 40 entries by randomly choosing among North America, Europe, and Asia using a random selection function. However, the choices are not equally likely. North America is given a very high probability of 80%, while Europe is set to 15%, and Asia to only 5%. This intentionally skews most entries toward North America and serves as a clear example of sampling bias in the dataset. We are creating income levels for a synthetic dataset by randomly assigning each of 40 entries to one of three categories: low, medium, or high. To introduce bias, we set the probabilities so that medium is chosen about 80% of the time, while low and high are each chosen about 10% of the time. This intentional imbalance limits diversity in income levels and is used to demonstrate how sampling bias can appear in data. We create churn labels using a random choice function that generates a binary array of zeros and ones, where each value indicates whether a customer has churned. The array is the same size as the dataset, so every customer receives a label. We set the probabilities so that about 70% of customers are labeled as not churned and 30% as churned. This intentionally imbalanced setup helps us study how a skewed churn distribution can introduce or reveal bias in the dataset. We are building a pandas data frame from the synthetic data arrays we created earlier. This data frame includes columns for age, region, income level, and whether the customer churned, each filled with the matching values from our arrays. Organizing the data in this tabular form makes it easier to work with. Once in a data frame, we can efficiently manipulate and analyze the dataset using pandas data handling tools. We begin by printing a short message to indicate that we are about to look at some sample rows from the dataset, which helps us focus on its structure. Then we call the dataframe's head method to display the first 5 rows. This quick preview lets us confirm that the data loaded correctly and gives us an initial sense of how the dataset is organized and what kind of information it contains. We are counting how many times each unique region appears in the region column of our data. This produces a simple frequency distribution that tells us how many entries belong to each region. Because we are not normalizing these values, we are looking at raw counts instead of proportions. This helps us understand the absolute distribution of regions in the dataset. We examine the dataset by calculating the proportion of entries from each region to check for sampling imbalance. To do this, we count how many times each region appears and convert these counts into proportions, then round them to 2 decimal places for clarity. This allows us to quickly see whether any region is overrepresented or underrepresented, which can reveal potential bias in the data. The code finds the proportion of each income level in the dataset by counting how often each level appears and converting those counts into percentages. It then rounds these proportions to 2 decimal places to make them easier to read. This helps reveal how income levels are distributed in the data and whether there is any imbalance or bias in that distribution. We introduce the output by stating that we are looking at region counts and proportions, then show how many entries fall into each region category. After that, we present the proportion of each region as a percentage. Together, these summaries help us quickly see whether some regions appear much more or much less often than others. This is important for detecting potential bias in the dataset, since overrepresented or underrepresented regions can affect the validity of any conclusions we draw. We begin by printing a new line and a clear label that says, "This section shows income level proportions," so the output is easy to follow. Then we display the values that represent the proportion of each income level in the dataset. Looking at these proportions reveals how income levels are distributed, which can expose biases or a lack of diversity. This helps us judge how representative the dataset is in terms of income levels. This script creates a small synthetic customer dataset to demonstrate sampling bias. It randomly assigns ages, then heavily favors North America for the region, with only a small share from Europe and Asia. Income levels are mostly medium, with few low or high incomes, and churn is a simple yes or no label, with most customers not churning. The script prints sample rows, then calculates and displays counts and proportions for regions and income levels. By highlighting these imbalances, it shows how biased sampling can appear in collected data. In this lecture, you learned to describe the typical tabular structure of a basic machine learning dataset, distinguish between common data types such as numeric, categorical, and text, and evaluate simple datasets for obvious quality issues that could affect learning. In the next lecture, Lecture B, we will go over features and targets.
Thank you for your attention. See you all in the next lecture.